let's look at some proofs of these problems. So in looking at the controllability, we have a number of tests. I'm not going to prove them all, but I want to prove a few because I think it's helpful, instructive. So here's the first test. And again, I'm looking at the discrete time problem. I'll come back and look at this similar test in continuous time. So this basically says the range of the control map is equal to Rn. So that's actually what our definition of controllability is. If and only if our controllability Gramian is positive definite for some t greater than 0. Okay. Notice it doesn't specify what the t is. It just says there is some t for which this is positive definite. So here's the proof. So we note by properties of the pseudo-inverse, first of all. So if I have the matrix, the control map B, so again, that's just a matrix. So I'm suppressing the dependence on time. Then a property of the pseudo-inverse says that B is equal to B pseudo-inverse B. That's just a property. Another property says that B pseudo-inverse B is self-adjoint. Okay, this is self-adjoint, and so the adjoint of this is given by this. So anyway, this is just the adjoint of this, but it's self-adjoint. So in other words, this quantity itself is also equal to this. And so if we look at the range of B, because B satisfies this, it's equal to the range of B pseudo-inverse B. But B pseudo-inverse B can be shown to be equal to this. Okay, and so notice I have B pseudo-inverse times something. And so this matrix, the range of this matrix, is contained in the range of B adjoint itself. In other words, I have this extra thing over here. So, but notice how out front I have B adjoint. And so the range of this is contained in the range of this. Okay, so what we've shown here is that the range of B is contained in the range of B adjoint. Similarly, if we start with B adjoint, we can see that I have B out front here. So this the range of this is contained in the range of B alone. Okay, so I've shown that the range of B is contained in the range of B adjoint. The range of B adjoint is contained in the range of B. Therefore, the range of B adjoint is equal to the range of B. Okay, so clearly that's going to be important here because the range of this and the range of that are important. They're obviously related. So the range of B is equal to all of Rn if and only if K is non-singular. Okay, in other words, the only way this can be all of Rn is if the range of this is all of Rn, in which case this is a non-singular matrix. So we know that because of the way it's formed, because of the way K is formed as B adjoint, that it's at least positive semi-definite. Okay, there's no way I can get a negative eigenvalue out of this. All right, but having zero determinant then in this matrix would mean that the range of B is not all of Rn, because the range of this is the same as the range of that. And so because of the fact that it has full range, if and only if this has full range, then this must be in fact positive definite. Okay, so we have proved that result. Boom. Nice. All right, the next test. For some t, the controllability Gramian is positive definite if and only if the rank of the controllability matrix is equal to n. Okay, so we first established the fact that for K of the controllability Gramian up to time n is positive definite if and only if the controllability Gramian up to time t is positive definite for some t. Now clearly, if the controllability Gramian up to time n is positive definite, then the controllability Gramian up to time t is positive definite for some t, because this obviously holds when t is equal to n. So that's that direction. So notice we're proving if and only if. So we've proved this side now. Now we're going to prove the other direction. Now, recall that the control map has composition rules. And so you can show that K up to time, that the controllability gradient up to time t can be given by either of these, by these two expressions, depending on whether t is less than n or t is greater than or equal to n. Okay, so if for some t less than n, K up to time t is positive definite, then K up to time n is positive definite by this composition. Okay, so if t is positive definite for t less than n, so that's this case here, this first case. So if this is positive definite, then I can take this over to the other. This quantity is positive semi-definite, and so when I take this over to the other side, I have something positive definite plus something positive semi-definite, and that's Kn. So that proves that Kn is going to be positive definite, okay, because this is already positive definite. So that's for t less than n. Now what about t greater than or equal to n? So if for some t greater than or equal to n, K at t and 0 is positive definite, then notice that in this case we have used this property that the range of the controllability gradient up to time t is equal to the range of the controllability gradient up to time n for t greater than or equal to n. So if this is positive definite, then that must be positive definite. Okay. On the other side, then, since K up to time n is given by the controllability gradient times the controllability gradient adjoint. Okay, so up to this point, we have proved that this condition is equivalent to saying that the controllability gradient up to time n is positive definite. Okay, so in other words, instead of using this condition now, I'm going to use this other condition, that is the controllability gradient up to time n. So the controllability gradient up to time n is given by is related to the controllability matrix this way, and so the controllability matrix, which is given here, has range all of our n if QC has range all of our n because of the property that I showed. And so the rank of this must also be n. So we have this relationship. And so we've proved this test. Nice. What about the continuous time controllability? Remember, the continuous time controllability uses the controllability gradient is a convolution integral type thing. So we have this test. For t greater than 0, the controllability gradient is positive definite if and only if the rank of QC is equal to n. So we have the same kind of problem, but now our controllability gradient isn't a matrix, right? It's not a, well, it actually is a matrix, but it's not a matrix it's easy to identify as a matrix times another matrix. Okay? In fact, the controllability gradient is an integral. So we have that. Okay, so for any v non-zero, actually for any v, we have this, that v adjoint the controllability gradient continuous times v can be written as this integral. Okay, so I have b adjoint. Okay, so notice that when we have b adjoint times v, that gives us a control signal, a continuous time signal. Operating now on it by the control map, I get a vector in Rn, and so this is a vector in Rn adjoint times a vector in Rn, and so it's a well-defined quantity. I can integrate this now between 0 and t, and so expressing this, I can show that this quantity can be written this way. Notice that it involves e to the at minus tau, and its transpose. Okay, and so if I look at this quantity and this quantity, this is the transpose or the adjoint of this. And so I have this quantity times its adjoint. And so I can show that that's the norm of this quantity squared. And now I integrate that from 0 to t. I can change the variable now in this. Instead of using t minus tau in here, I can simplify this by using a change of variable. Instead of using tau, I can use tau is replaced with t minus tau, and I change the integral around, and I can get this integral. So by change of so even though I'm using the same variable names, tau and t, well, actually tau, I've actually done a change of variables, okay, in going from here to here. So I have this quantity. All right. So it's like, all right, so what does this mean? Well, this quantity right here, v transpose e to the a tau b, is an important quantity. So we're going to look at that in more detail. In particular, we're going to look at the derivatives of that. So if I differentiate this with respect to tau, notice that this is the only part that depends upon tau. The b and the v adjoint do not depend upon tau. And so e to the a tau d tau is e to the a tau times a. Remember, these two actually, e to the a tau and a actually commute, so I can put it the other way, or I can put it this way. I'm going to put it this way for a particular reason. So that's the first derivative. The second derivative, if I differentiate this now with respect to tau, I'm going to get this. I can keep differentiating. I'm going to differentiate all the way up to the n minus first derivative. That's what this is saying. D to the n minus 1 means n minus first derivative with respect to tau of this quantity. So I just keep differentiating, and each time I differentiate, I'm going to get another power of a. So I've differentiated n minus 1 times. I'm going to get n minus 1 power of a here. Okay, so this is just a property of this function, v adjoint e to the a tau b. Okay, I just get this. Now, so it's like, okay, so what? Well, I'm going to next stack these equations side by side. So I have this quantity, I have the first derivative, second derivative, all the way down to the n minus first derivative. And I notice that when I look at these expressions, that all of them are going to have v adjoint e to the at out front. So I can pull that out of the entire matrix. And when I do, voila, what pops out but the controllability matrix? Boom. All right, so I have this quantity times the controllability matrix. So now I'm in a position to talk about the relationship between the controllability Gramian and the controllability matrix. Now notice this vector here, since e to the a tau is non-singular for all a and for all tau, okay, which is pretty cool. In fact, I can even give you the inverse. The inverse of e to the a tau is e to the minus a tau. Okay, so I know so it's not only invertible, but I even know the inverse. Okay, so that's just pretty cool. All right, since this matrix is non-singular, then this vector w is non-singular if and only if vector v itself is 0. Okay, so we have that property. All right, so there is a non-zero vector such that v adjoint kv is 0 if and only if this quantity is equal to 0 identically. So that's what this triple line equals means, identically 0. So it's a function of time. What it's saying is that as a function of time, this is equal to 0 for all values of tau. Okay, for all values of tau in this interval between 0 and t. So this is a function of tau, and it's equal to 0 for all values of tau in this interval. Okay, so I have this function that's 0, and so since it is 0, identically 0, the derivative is 0. So it's a constant, right? And so its first derivative is 0, and it's a constant, which the next derivative is 0. And so you can show that the function and all its derivatives must be equal to 0 on this interval. So not only is that function 0, but all its derivatives are 0 on that interval. So as a result, this function is identically 0 if and only if this vector, which is non-zero, is in the left null space of QC, right? Because we showed that this and all its derivatives give this quantity times QC. And so all of that is equal to 0 if QC has a vector with a left null space in the left null space for all t. So by contrapositive argument, there exists a non-zero vector such that V adjoint KV is equal to 0 if and only if QC is singular, and that is, it has rank strictly less than n. So it should say is singular. So we have that expression of controllability, and now we have proved it. Cool. Next, we look at theorem 23.1, which says that R, which is the range, that the reachable space is the range of the controllability Gramian. The range of the controllability Gramian. So how do we prove that? So basically, these are two sets. And so in order to prove that these two are equal, I need to show that this set is contained in that set, that this set is contained in that set. Okay, so we want to prove that R is contained in the range of the controllability Gramian. Now, this condition is equivalent to its complement. So that is that the perpendicular, or the orthogonal complement of this is contained in the orthogonal complement of the reachable set. Okay, so sometimes it's easier to prove things by their negative. So if this is the case, then this is the case. So if and only if. There's that if and only if condition. So, but it turns out this is going to be easier to prove. And so often what happens with controllability is it's easier to prove uncontrollability things than it is to prove the actual controllability thing. So that's actually what's going on here. We're actually proving an uncontrollability thing. All right, so let V equal the range of the controllability Gramian perp. So it's perpendicular to the range of the controllability Gramian. So since it is perpendicular to this, we can go through and show that this must be 0. Okay, so that is a consequence of the fact that I have the orthogonal subspace. So V adjoint KV is 0. If and only if, again, this integral, we've gone through and shown this integral is 0. If and only if this quantity is equivalent to 0, identically 0, which is true if and only if this quantity itself is equal to 0 for any u. Okay, so this is equal to 0 identically if this is, so notice that I have V transpose e to the at minus tau b under the integral sign. So if that's equal to 0 for all tau, then it's certainly true regardless of what input is in here. Okay, so if x is in the reachable space, there exists a u that gets you there. And so for V in the orthogonal space of the controllability Gramian, I take the inner product of this x and V. This x and V is, here's the inner product. X is given by this, but I already know that this is equal to 0. And so notice that x is any element in this space, and when I take the inner product with V, which is in this space, I get 0. So V is in the orthogonal complement of R. Okay, so I started off with V in the orthogonal complement of the controllability Gramian range, and I end up with something in the orthogonal complement of R. So that shows that this set is contained in this set. Phew, it's like kind of twisted. Seems a little twisted, but that's just how it goes. So anyway, that is proved. Now we prove the other direction. Let V be in the range of the controllability Gramian. That means there's some W such that V is equal to the controllability Gramian times W. We pick as our control signal this. Okay, and so when we apply that to the system, x at time tf is given by this expression involving w, actually involving all of this. Okay, so notice that the w is a constant, and so I can take that outside the integral, and so the integral results in the controllability gradient times w. But the controllability gradient times w is just v, and so x at time tf is v, which is, since this integral, anything that comes out of this integral is in the reachable space, then v must be in the reachable space. Since we started off with something in the range of k and we ended up with something in the reachable space, we've shown that the range of the controllability gradient is contained in the reachable space. So there we go. Wow. Next, we move on to the energy inequality. So here's our energy inequality. We want to show that the energy in the control signal is given by this expression, satisfies this inequality, with equality if U is a particular value associated with X. So in order to do this proof, I'm first going to define what is called the truncation operator. So the truncation operator operates on a control signal and gives us something that's a control signal. So notice it's mapping from one space to the same space. Okay, and here how it's defined. Okay, so operating on a signal, it's going to define, so it's going to truncate the signal outside this interval. Okay, it's going to truncate the signal outside this interval. It's going to set it to 0. Okay, so in general, I could have in my space a signal that goes on forever. What this is going to do is it's going to truncate it between time t0 and t. Now, this is as an operator, it's actually an orthogonal projection. Now, it's kind of weird because as an operator, it's an integral. I mean, it's an operator on a continuous function of time. Okay, but I notice I've truncated between time t0 and t. Okay, so it's 0 outside of that interval. If I truncate again, I get the same thing back. I can truncate it as many times as I want, and I still get the same thing back. Okay, and I can actually go through and show that it is actually a self-adjoint. So remember, the input space to this is U, and it maps back onto itself. If I started here and map backwards, then that's basically what an adjoint does. Okay, and so I can show that these are adjoint, self-adjoint. I can get various combinations of them coming out. So this is an orthogonal. So it's a kind of a different. It's not a matrix. Okay, this projection is not a matrix. It's a truncation operator in it, but it satisfies all the properties of an orthogonal projection. So we can also show that the way our controllability control map is defined, that the control map, remember, is defined as an integral from t0 to t, right? And so by the fact that we're truncating our signal from t0 to t, we're only looking at that part of the signal anyway. So the control map operating on signals that come into this projection operator is the same as if we just applied the control map directly. Okay, and so we can see that the 2 norm of this signal is just given by this expression itself. It's just the norm of U itself. I'm sorry. The U itself may go on beyond t0 and t. So this projection is just this from t0 to t integral squared. Okay, so that is that's the truncation operator. I'm going to define another operator, okay, that is given by our truncation operator minus this operator. Okay, so before, when we looked at B, we looked at B B adjoint. I'm sorry, B pseudo inverse. Now I'm going to look at B pseudo inverse B. So that is, I'm operating in the opposite direction. And I'm going to define this. So this is an operator. I can define it if I want. I can define it if I. So here's this operator. And I can go through and show that it's given by this. I can also go through and show that this is also an orthogonal projection. So E naught is a projection, an orthogonal projection. This is an orthogonal projection. I'm sorry, this is an orthogonal quantity. I'm sorry, self-adjoint. This is self-adjoint. But we can go through and show that because of the way E naught works with B, that this is in fact a projection. That is, if I do this and do it again, I get the same result as if I just did it. So anyway, this is an orthogonal projection. So it's a little complicated. So I can go through and show that I have this condition satisfied. So E naught is equal to E naught adjoint E naught. And so I have this situation. So that would be just by taking this over to the other side. So if X is the control map operating on a control signal, I can show that E naught operating that is restricting the attention of U from T naught to T, and looking at that norm squared, that's this quantity, right? But this quantity, using this operator, can be written this way. Okay, so notice I'm operating on U this way. So I have this quantity, and so this quantity here is given by this. So BU is X. This is the norm of EU squared, and so I have this relationship. Okay, so the energy in the interval between T naught and T can be written this way in terms of this new operator, energy squared, plus this quantity. So as a result, this quantity is equal to this. Again, I just showed that. But this in general is going to be greater than or equal to 0. And so all of this is given by this. And so that is where the inequality goes. Okay, so this is actually the integral from T naught to T of the norm of U of T squared, and it's greater than or equal to this. So that's the inequality part. We get equality if and only if this is 0. That is, this is equal to this if and only if this is 0. But E operating on U, so this is E operating on U, and this is 0, if and only if EU is equal to, and again, B pseudo inverse B is given by this expression. This quantity is X, and so we have this expression here. E naught U is equal to this. So we've shown the proof of the energy inequality. So that's sweet. Okay, in talking about controllability, we introduced the notion of a cyclic matrix. And we said that a matrix was cyclic if the matrix A is cyclic if there's some non-zero X such that this matrix, which is like a controllability matrix, has determinant non-zero. And so the claim made was if two matrices F and G are both cyclic, that there is a transformation that relates, and they have the same characteristic polynomial, then there is a transformation matrix that relates the two, that shows that they're similar. Okay, so let's prove that. So we start off with F and G both being cyclic. So that means there's some X and Y, so that this matrix involving F is non-singular. So this is like a controllability matrix involving F and X. This is like a controllability matrix involving G and Y, and that should say QG, not 0. And so I have these two, QG and QF, both non-singular. So I can define this matrix T which is non-singular, and its inverse, in fact, is given by this. And so we can show then that the matrix H, given by this expression, is equal to this expression. And so I can show that F is given by this. Okay, so we can show that that there is a matrix H such that these two matrices are equal to each other. So notice, what are these things? So this is F and its controllability matrix, G and its controllability matrix. And so notice that the controllability matrix, in this case, which must be a square matrix, serves as a similarity transformation. So this similarity transformation is equal to this similarity transformation. And since these two are equal to each other, I can multiply on the left by QF, on the right by QF inverse, and I get this quantity, where T is given by this. So I have shown this. Now, an important thing with cyclic matrices is if we look at their, using Cayley-Hamilton theorem, remember Cayley-Hamilton theorem says that a matrix satisfies its own characteristic polynomial. So that is, we can solve for the highest power of a matrix in terms of the coefficients of the characteristic polynomial and the lower powers of the matrix. So I have this relationship. And so if I multiply this by x, I get this, which I can factor this way. And notice when I factor this, I get my QF coming out, popping out of this. And then I have this vector alpha, which includes the coefficients of the characteristic polynomial. So we have that situation. Okay. If now I look at F times the QF matrix. Okay, so here's the QF matrix. If I multiply this on the left by F, notice that what that's doing is it's basically raising all of these F's to the 1 power. Okay, and so if I now take that product and multiply it by the nth identity matrix. Okay, so if I take this matrix now and I multiply by F, notice that this last element over here, since it is now F to the power n times x, but F to the power n is all of this stuff times x. Okay, and so I can see then if I just pick off that last element, I get F to the power n times x. But F to the power n times x is equal to QF times alpha. Boom. So I get that. So I'm taking this quantity, I'm multiplying by the identity matrix column that's basically all zeros and then a 1. So this is just picking off the last column of this matrix. So if I take this quantity now, and since QF is invertible, multiply on the left by QF inverse, I get this. So alpha is equal to all of this stuff. So notice that QF inverse F, QF, that is the matrix H that I was talking about. Or actually I should say C. Well, anyway. If I look now at so if I take this matrix and multiply again by F, okay, basically what that, so multiplying by F, this guy is what that was, okay, in other words, I can think of these columns as being shifted over one by one in this process. And so I can show that if I pick off the kth column of this matrix, okay, I get this, F to the power k times x. So that is, I'm getting this element. This is what I get when I multiply this out. And I can also show that that's equal to the column just immediately on the other side of this. So that is, if I pick off the other side of QF, this is what I get. So I have this relationship here. Okay? And so I can now define this matrix C, or actually H. And so we have this. F times QF is equal to F times QF times the identity matrix. So notice that these are the columns of the identity matrix. I'm just stacking them one by one. Okay? So I'm going to distribute this now through this identity matrix. And so I'm basically multiplying each column of the identity by this matrix FQF all the way through. But I notice that this quantity is equal to this quantity. Okay? That was one of the properties that I showed. So that is, this quantity is basically picking off the previous column. That's what this is doing. And so forth, all the way down to the n minus first term. Okay? And finally, this quantity gives us this. And so we've gone through and shown this for the result. So notice that QF appears in every term in this matrix. I can factor it out. And I get this quantity, identity, the second column of the identity, third column of the identity, times alpha. But I can go through and show that this matrix is exactly what we called C. Okay, so this is the second column of the identity, third column of the identity, so forth, all the way to the nth column of the identity. And this is QF times alpha. Okay, so that's just alpha, QF times alpha. So this is what I get. And so I have this relationship is equal to this. I can solve for C, and this is what I get. Similarly, I can do the same thing for G and Y. I can show that G to the power n times Y can be written this way. Again, I can show that C is given by this expression, and so since C is given by this expression and by the other expression, I can find a similarity transformation that relates the two. Whew. These are some pretty intense things. There's a lot of really deep stuff going on here. But I'm going to stop here for now. I think your brains have had enough, at least as far as the proofs are concerned. We'll move on to some practice problems.